Hello everyone, my name is Raj and today I'll be talking about masking corruption packet losses in data center networks using link local retransmission. This is a joint work with my collaborators Chavan, Shinzer, Nishant, Ayush and my advisors Manchun and Ben. Packet loss in data center networks is an important problem. It is well known that packet loss degrades application performance and that has a direct impact on revenue. Now, packet loss is mainly caused by congestion as well as link local corruption. There has been significant prior work to mitigate the packet loss that is caused due to congestion, but not so much due to link local corruption. Therefore, in this paper, we'll be focusing on mitigating the impact of corruption packet loss. So why do we care about corruption packet loss? It turns out that in practice, corruption packet loss can be significant. A last case study by Microsoft, consisting of 350,000 links across 15 data centers, showed that the number of packets that are lost due to corruption are comparable to those lost due to congestion. Another study by Alibaba Cloud showed that about 18% of the packet drops that seriously affected its cloud customers were caused due to corruption. And like any other loss, corruption packet loss leads to increase in tail flow completion times as well as drop in throughput. So how can we fix corruption packet loss? Well, performing a physical repair of the link that is corrupting packets is the only true way to fix corruption packet loss. But this can take between several hours to days. And until then, what we can do is mainly to mitigate or mask the effects of corruption packet loss. Now, there has been some prior work to mitigate corruption packet loss, the state of the art approach being to disable the corrupting links. Now, the main drawback of this approach is that all the corrupting links cannot be disabled due to network capacity constraints. Data from Microsoft Data Center shows that about 15% of the corrupting links cannot be disabled. In this paper, we revisit the classical loss recovery strategy of link local retransmission because it does not face this limitation. Now, link local retransmission is not a new idea. It has been widely deployed previously in wireless networks, but to the best of our knowledge, it has not been revisited in the context of data center networks. We believe this is because of challenges that are unique to the data center context. Now, to understand why is it challenging to do link local retransmission in a data center context, let's look at a basic link local retransmission scheme. In the example network here, the link between switch 2 and switch 3 is corrupting packet. Now, the basic link local retransmission scheme can be imagined as a protocol that runs between a sender switch and a receiver switch. The sender switch basically adds link local sequence numbers to the packets that are being sent on the corrupting link, and it also makes copies of these packets and buffers them. Now, suppose packet number 2 is lost due to corruption, then the receiver switch can detect this loss based on the missing sequence number and inform the sender switch that packet number 2 was lost while everything was received until packet number 4. The sender switch can then retransmit packet number 2 with high priority and then drop the copies of the buffered packets that have been successfully delivered. Well, this works, however, it is insufficient in the context of data center networks. Why? For starters, this very simple scheme does not preserve packet ordering. One of the challenges in today's data center networks is the use of RDMA flows. RDMA is very sensitive to packet reordering, and any small amount of packet reordering can significantly degrade the FCD performance of RDMA flows. Therefore, we need to be able to preserve packet ordering and do so at high link speeds. Another challenge in today's data center networks is that the switches use shallow buffers and therefore any buffer overhead has to be kept to a minimum. Finally, the third challenge arises from the fact that flows in data center networks are very short. Now, when short flows face packet corruption, there is a higher probability that the tail or the last packet is lost. Consider this example where a short flow of 4 packets loses the last packet. Now, because the receiver detects the loss based on the missing sequence number, in this case, it is unable to detect this loss until a subsequent packet is transmitted on this link, and this packet can be transmitted after an arbitrary amount of delay. Such situations lead to retransmission time or for end-to-end transport, and that can lead to high flow completion times. Therefore, we need to be able to detect and recover tail packet losses and do so as quickly as possible. In this paper, we propose Link Guardian, which addresses all these three challenges by first using the basic link local retransmission scheme described above and then building three key techniques on top of this scheme to address the three challenges. In this talk, I'll be talking about Link Guardian's technique to handle tail packet loss, while for other techniques, you can refer to our paper. So how does Link Guardian handle tail packet loss? Here we show the internals of a sender switch which consists of two queues, one for the normal packets and another higher priority queue for retransmission packets. Now when a tail packet loss occurs, basically the normal traffic goes idle and the latest transmitted packet, this packet number 4 in this case, is lost. The standard technique to deal with such a scenario is to retransmit the unacknowledged packet, which is packet number 4 here, after a certain timeout. However, the problem with timeouts is that they need to be set very conservatively, otherwise we risk spurious retransmissions. To avoid all these issues regarding setting a timeout, in Lingardian we take a timeoutless approach. Our key idea is that if we can send a dummy link local packet when the traffic goes idle, then we can help the receiver switch to detect the tail packet loss. To do so, we introduce another lowest priority queue which consists of a single dummy packet. Now when there is normal traffic, this queue is automatically paused because it's lowest priority. However, whenever the traffic goes idle and there is a tail packet loss, the dummy packet queue is automatically resumed. At this point, we add the next sequence number to the dummy packet and transmit it on the corrupting link. We also create a copy of the dummy packet and put it back into the dummy packet queue. Now this dummy packet allows the receiver switch to detect the tail packet loss while and then it can inform the sender switch about the same. While the copy of the dummy packet helps to replenish the queue for future tail loss detection. The beauty of this approach is that tail losses are detected near instantaneously and then there is no extra overhead because dummy packets are sent only when the link is idle. LinkGuardian is implemented on an Intel Tofino switch in around 1800 lines of P4 code, and we evaluate it on a hardware testbed consisting of Intel Tofino switches and Xeon servers equipped with 100 Gbps NICs. We also use a special instrument called the variable optical attenuator to introduce a corruption loss rate of 10 to the power minus 3. In evaluation, we consider two variants of LinkGuardian. LinkGuardian, the default variant that preserves packet ordering, and LinkGuardian NB, NB standing for non-blocking, is basically a light version of LinkGuardian which does everything that LinkGuardian does except preserves packet ordering. Here we show the main result of LinkGuardian, that is, it improves the tail flow completion times for TCP. The graph here shows the CDF of flow completion times for 24 kb flows when there is no loss. On introducing a corruption loss rate of 10 to the power minus 3, we can clearly see a long tail in the FCT distribution. If we enable Link Guardian on this link, we can see that it improves the 99.9th percentile FCT by 19 times and the performance nearly matches the no loss case. Instead of Link Guardian, if we enable Link Guardian NB, surprisingly we can see the nearly the same improvement even without maintaining the packet ordering. The reason for this result is that when TCP flows are short, any reduction in congestion window due to out of order retransmission has a minimal impact. You can find more detailed analysis on this result in the paper. As for the RDMA flows, Link Guardian improves the 99.9 percentile FCT by 39 times and we show detailed RDMA results in the paper. LinkGuardian's main cost is its consumption of packet buffer overhead to buffer packets. Here we show the results of a stress test at 100G line rate traffic. We can see that when running LinkGuardian, the amount of packet buffer consumed by both the sender and receiver switches is less than 90 kb, whereas while running LinkGuardian non-blocking, the cost is much lower, less than 25 kb for the sender switch, and there is no buffer overhead at the receiver switch. To put this result in context, switches today have tens of MBs of packet buffer. To summarize, in this paper, we propose Link Guardian to mitigate corruption packet loss by performing selective in-network recovery at sub-RTT timescales. Link Guardian handles tail packet loss without employing any timeout, and it is able to preserve packet ordering for reordering sensitive RDMA flows. Overall, in this paper, we demonstrate that link local retransmission is both practical and effective in today's data center networks, and that out-of-order retransmission is sufficient for short TCP flows. Thank you, and I'm happy to take any questions.